Okay, hello, I'm Alec, and today I'm going to talk about some work that I did with Edward and Kai on some new direct sum tests. So first, we're going to be talking about property testing in this talk. Let me just define what that is. We have some class of functions, for instance, Boolean functions on the hypercube, and a property is just some subset of those functions. For instance, it might be the Boolean functions which are XORs of a subset of the bits. And in a property testing question, we're given oracle access to some function f, and we want to distinguish between two cases, between f having the property and f being far from having the property. So in this picture here, we're just going to get something from this entire space of things, and we want to accept the things in this little green region, and we want to reject the things outside of it. This notion of distance here, this farness, we usually define it by the fraction of inputs on which two functions disagree. So that's the distance between two functions, and the distance from f to the property is just the distance from f to the closest function that has the property. The reason we need this red buffer region is because our goal in property testing is to get an algorithm that is very query efficient. So it looks at a very sublinear amount of the domain. But if we had no buffer region here, then it could be the case that we take a function and modify it in one place to break having the property. So that would be just really prohibitively expensive to test. So instead, we have some kind of buffer region, and this generally allows us to hopefully get algorithms whose running time does not depend on the size of the domain. It only depends on this parameter epsilon. Okay, so that's the basic property testing setup. And for some intuition, let's just consider one of the classic property testing questions, which is linearity. So we're going to say that a function on f2 to the d to f2 is linear if it's a sum of some subset of the bits. A fact that everyone knows is that a function is linear if and only if it satisfies this property. And so this is a nice property, and it turns out that there's something kind of pretty similar to this property that lets you actually get a tester for linearity. So the classic BLR linearity test works as follows. You sample two random points, x and y, and then you check whether or not they satisfy this identity here. F of x plus f of y is f of x plus y. So by virtue of fact one, this BLR test is always going to accept linear functions. And it might be less obvious why this is the case, but it turns out that if f is far away from linear, then there are no functions which are far from linear but still have f of x plus f of y equals f of x plus y on most random inputs. So specifically, we're going to reject epsilon far functions with probability omega epsilon. And that's kind of the best thing you could possibly hope for. Okay, so that's the story with this classic property of linearity. And what we had thought about was, in our work, was a certain generalization of linearity to grid domains. So a grid domain is just, instead of 0, 1 to the d, it's maybe 1 through n to the d, and we're still having a Boolean output. And we're going to say that such a function on the grid is a direct sum if we can decompose it to functions which only look at one coordinate of the input at a time. So there's several reasons you might want to study direct sum testing. It's a natural generalization of linearity testing to the grid. And there's also some connections to PCPs and direct product testing, which makes this a pretty natural object of study. And this has been studied before. In 2019, Dinner and Golubev gave a nice tester for direct sum, and they proposed a tester that was another tester for direct sum testing, which we decided to call the diamond test, and they asked to analyze or kind of refute this as being a tester as an open question. So what we did in our project is we analyzed this diamond test that was introduced by Dinner and Golubev, which gives a new tester for this fundamental property. And along the way, we figured out how to get some direct sum testers that have additional nice properties, such as erasure resilience and being more randomness efficient. But finally, I think the really interesting thing about our work is that by kind of getting a tester for this fundamental property, we're able to understand things about functions more. So one really neat thing that we were able to show is the fact that that we have this tester that is sound and complete with certain parameters implies a certain Fourier analytic fact, which this might almost seem backward. Usually we might want to use some nice Fourier analytic fact to prove the validity of our tester, but here we did it the other way around, which I thought was kind of interesting. So that's kind of what we did in our work, and now let me tell you what we're gonna do in this talk. I'm gonna present the 3 key ideas for the analysis of the diamond test on the hypercube. The full analysis over the grid is pretty similar, but just to keep it simple, we're going to think about the hypercube. And the reason I'm going to show you these 3 ideas is that I think that the proof framework is very powerful in general. All the parts aren't really novel, but hopefully seeing them together, you can get some intuition for why they're really powerful and nice together. And I hope that this can be useful if you have any property testing questions that you're thinking about. In giving this talk in the past, someone who listened to it was able to solve one of their property testing questions. So without further ado, let me define this diamond test and tell you how to analyze it. The diamond test is based on this thing called the interpolation function. So the interpolation function takes in 2 bit strings, A and B, and it is kind of parameterized by some other bit string, and it tells you to take some bits from A and some bits from B. So specifically, if we have phi x of A, B, we'll take the A coordinate whenever x is 0, and we'll take the B coordinate whenever x is 1. So here we have an example. If the interpolation string is 0, 1, 0, 1, 1, then we'll take A1, B2, A3, B4, and B5 if we're doing this. And if you flip the coordinates, you'll get kind of the opposite things for what you take. Okay, so this is the interpolation function, and the diamond test is going to work as follows. We're going to take random A and B, and then we're going to take a random x, and then we're going to test whether or not f of A plus f of B is the same as f of the interpolation of A and B by x plus the interpolation of B and A by x. So one nice, I guess, initial sanity check is this fact up here, which says if f is actually an affine function, then then this equation will always be satisfied, and if this equation is always satisfied, then f is affine. Maybe a pretty easy way to see why this would be satisfied for affine functions is if we go back to here, if we do f on this top thing plus f on this bottom thing, and we have something which is a direct sum, then it's just going to decompose into f of a1 plus f of b1, or like it's going to decompose into these functions that just look at one of these bits at a time, and so it doesn't matter if we permute the order of, or like permute whether or not those bits are present in the first thing that we're applying f to or the second thing. And I want to highlight for a second that one reason why this test is pretty interesting, it feels pretty different from the kinds of things that we were doing in the standard BLR test. So the BLR test, you have some kind of addition that you're doing, but here we're just having a permutation. So obviously the BLR test doesn't really make any sense over grids, because there's not really a nice way to define the notion of addition. But this test would make total sense if A and B, instead of being bit strings, were kind of elements in a grid domain. This notion of kind of shuffling the things between the two, shuffling whether or not something's in A or B between the two things, that's still totally legal in the grid. So maybe that says that this is kind of a pretty interesting tester, and it's pretty different than the BLR test. And it also makes it harder to analyze for some reasons. So anyways, so this is the diamond test, and we've already said that it always accepts affine functions. So the rest of the talk is going to be devoted to telling you why, if the diamond test accepts with good probability, then it means that your function is close to affine. Or in other words, to say that this thing rejects functions which are far from affine. And in this theorem statement here, the important thing I want you to note is that we don't have any dependence on the size of the domain. We just have some constant or order epsilon closeness is what we'll get if you pass with probability 1 minus epsilon. Okay, so that's really great. And now let's get on to the proof. So as I said, the proof is going to have three key ideas. And the first idea is to take the diamond test and instead think about this thing called the four-function diamond test. So in the four-function diamond test, we now have four functions, and we have the same inputs as before, this a, b, and then these two interpolations, but now we're applying to them these four different functions. And this might seem totally insane. The diamond test we already didn't know what to do with. Why is it going to be better to think about now four functions? The motivation, I guess maybe it's kind of hard to see right now, but it turns out that this is going to be better for induction. So more precisely, if we kind of fix one coordinate of ax, and b, then we can think of the four-function diamond test as being fixing one of the coordinates and then running a four-function diamond test on running a lower dimensional four-function diamond test. And it turns out that the one-function diamond test doesn't have this property. So that's why we're going to need to think about this seemingly much more confusing object. It's because it's going to give us a stronger inductive hypothesis. And just to maybe convince you that we're not doing something totally insane, I can assure you that we still have that nice property from before, which is that if this four-tuple of functions passes the diamond test with probability 1, then it actually means that these functions are all affine. And in fact, they're basically the same affine function. So this satisfying this thing seems to impose some structure on your function, and so maybe this is a reasonable idea. Okay, so now we're going to get into the second idea, which is the most important. So what we're trying to show is that functions which are far from affine get rejected with good probability by our tester. And we're going to kind of first think about a special case of a function which is somewhat close to affine. So it's 0.01 close here. And we're going to show that for these functions, specifically, the test will reject them with probability that's proportional to their distance to affinity. So ultimately, we'd like to just say that the rejection probability for any function is proportional to its distance from affinity. The motivation for starting with these things is twofold. So first of all, these things are comparatively easy because if you're 0.01 close to affine, there's a very unambiguous way to round f to an affine function. If we allowed f to be like half far from affine, then it's not really clear what you would do. But when f is this close to affine, you can think of the behavior of f as just being mostly agreeing with an affine function and then occasionally differing. And then the second reason is that somehow, even though what we really care about is all classes of distances, this is going to let us, in our full proof, this is going to be somehow an important part of the induction. So we'll understand why that is in a second, but first let's just prove this. Okay? Yeah, and I guess before we prove it, let me just comment. The reason I call this the dichotomy theorem is that what it's telling you is if the test passes with good probability, then either f is kind of very close to affine or very far. So, and later we're going to show how to get rid of this very far possibility. Okay, so as I just said, because f is close to affine in this case, we can think of f as kind of let's break the domain of f up into this white box and then a couple of these black regions. So these black regions are places in the domain where f differs from the nearest affine function to it. Okay. And we're going to make some kind of, when we run the test, we're querying f on 4 points. And some of these points are going to fall in the white region, where f agrees with the nearest affine function. And some of them will fall in a black region, potentially, where f disagrees with the nearest affine function. So let's think about what would cause us to accept and reject. First, if we get everything in the white region, then we're going to accept, because we would have accepted anything on the affine function, and if everything's in the white region, then we're the same as the affine function, so we'll accept. If we get exactly one thing in a black region, then we're going to reject, because then we're going to be different from the affine function in one place, and then that'll be detected in the test. A problem can happen is if we have 2 errors. If we have 2 errors, then we're going to get +1 twice, and unfortunately, modulo 2, this ends up being 0, so we won't notice. Okay, so if we could say, if it was true that the queries that we were making in our tester, the 4 queries, were independent, then we would have that the probability of exactly 1 error is proportional to the amount of error. This is like if the amount of error is epsilon, then the probability of having 2 errors, if errors are independent, is like epsilon squared. So that would be a really good situation. Unfortunately, our queries are actually highly dependent. If you remember, the way we make our queries is we have this point A and this point B, and then we do these things called interpolations of A and B, where we kind of take some bits from A and some bits from B. The point is, they're very correlated. The amount that these interpolated points agree with A and B is much higher than what a random point would agree with them on. So that might seem pretty unfortunate, but fortunately, there's a lot of work that's been done on understanding this graph called the noisy hypercube, and using hypercontractivity, we can still say that our query points are reasonably well spread out. So we end up basically just getting something similar to what we would have intuitively expected in this independence case. And that lets us kind of show that the rejection probability is high when we have a lot of error, but not too much error. Okay, so that was the dichotomy theorem that we just proved. And now to finish up, what we need to show is we need to kind of get rid of the second part of the dichotomy theorem. We want to show that if f is very far, 0.01 far from affine, then the test rejects the four tuple with constant probability. The way we're going to do it, as I've alluded to, is we're going to induct on the dimension. So if you try to kind of naively induct on the dimension, you might kind of have some deterioration of your rejection probability of like a factor of half each time you increase the dimension, and that would be awful. There's no way you would get a good quantitative bound like that. But somehow we're going to use the dichotomy theorem to avoid that deterioration. So the way we're going to do this induction is we fix a certain coordinate randomly for A, X, and B, and then we can think of the four-function diamond test as first fixing that coordinate and then running a lower dimensional diamond test. That's, of course, why we chose the four-function diamond test, and the reason why we couldn't just use the regular diamond test. Okay, so let's see more precisely how this induction works. We're going to start with the base case, which is when the dimension is constant. For constant dimension, we're just going to use the fact that the test rejects with non-zero probability when f is not affine. This is just that thing we said in the very beginning. Passing the test with probability 1 is equivalent to being affine. So I guess here we'll have some non-trivial probability just because the domain is finite of and bounded of rejecting. Okay, so that's the base case. In the induction step, we're gonna fix some dimension and assume the theorem for smaller dimensions. And the kind of an important thing we're going to use is if f is far from affine, then it cannot have more than a constant number of restrictions, which are very close to affine. Okay, this is this nice result, and it should be pretty intuitive. It seems like if f was close to affine on a lot of restrictions of a single coordinate, then there should be some way to just say that f is close to affine. So using this fact, we deduce, because our dimension is large enough, that there is some coordinate where the restrictions of f are both far from affine. And then we're going to think about two cases. First of all, if the restriction is very far from affine, then we can just apply our inductive hypothesis. Remember, the whole thing we're trying to show is that if f is this far from affine, then there's a good rejection probability. The second case we have to deal with, though, is that f is not quite this close, not quite that far from affine, but it's still reasonably far due to the corollary. And here, we're actually now going to use the fact that it's close to affine to apply the dichotomy theorem. Remember, the dichotomy theorem said once you get close to being affine, all give you a high rejection probability, proportional to your distance to affinity. So now we're going to get good rejection probability. So that's pretty neat. What we said is in this low distance case, it's kind of easier to think about because we can just think about f and the nearest linear function to it. And then we said for the high distance case, either we can do some kind of induction thing, or we get back to the low distance case, and then when we get back to the low distance case, we know how to handle that. So kind of once we're done with that, we have proved that if you pass the diamond test with this probability, then you are close to affine. And yeah, that's what I had to tell you about today. And I hope that these 3 ideas of sometimes generalizing to a harder problem in order to have a better inductive hypothesis, for instance, this 4-function idea, and the idea of thinking about a low distance case and proving a dichotomy theorem, and then doing some induction to deal with the high distance case. I hope that these 3 ideas are helpful. Thank you.